This is a high priority this year because our goal is to have a lot of time on the track to test and tune our vehicle. This will give us the ability to make these changes quickly and easily. Steel has been used successfully on CSUN cars for many years. It is strong and tough, easy to work with, inexpensive, and readily obtainable. The weight has been kept down by utilizing slender, thin-walled tubes. Aluminum is lighter in weight. However, it is not as rigid and is susceptible to greater flex and deflection. Sizing the part up to correct this negates the weight savings. It is also more expensive and more difficult to weld. Carbon fiber is very strong and very lightweight. However, it is very expensive and much more difficult to manufacture. Carbon fiber parts require a long lead time, and replacement parts could result in a significant time setback. Suspension components such as the upper A-arms and the push rods are vulnerable to damage in the event of a crash. Therefore, it is important to be able to quickly manufacture replacement parts if this occurs. Traditionally, the CSUN cars have utilized rising rate suspensions because rising rate increases wheel rate, optimizes spring travel, is controlled by the bell crank ratio, it gives a smoother ride over small bumps, and it reduces the risk of bottoming out because the system provides increased resistance as loads increase. An issue that must be addressed this year is the bell crank reliability. The right rear pivot bolt became loose. This could result in a catastrophic failure. Since this year's vehicle will experience extended testing, the components must be able to last through testing and competition. In addition, wear marks have been observed on the front bell crank half shorts because of contact and interference between the front sway bar linkages and the bell cranks at full compression, indicating that more clearance is needed. The advantages of using anti-sway bars are that they allow a softer wheel rate, they combat roll during cornering, and they provide adjustability of oversteer and understeer. As I said in the beginning, the anti-sway bar is a type of spring. Springs that are made of steel are heat treated to increase their stiffness. We will manufacture ours out of 4130 steel, which will then be sent out for heat treatment. They will then also be shock peened to increase their fatigue strength. In conclusion, this year's kinetics components will consist of linear springs, adjustable fluid shocks, bell cranks, push rods, rising rate suspension, and front and rear anti-sway bars. This design meets the team goals without requiring major changes. At this time, I'd like to turn the presentation over to Sean Parker, who will speak on unsprung mass.
Great. My name is Sean Parker. I'm the unsprung mass engineer for this year's formula team. So I'd like to start off with what is the unsprung mass and what does it do. It is basically all the components and hardware that are not supported by the suspension. The idea is that it transfers the forces from the ground into the kinematics of the suspension. The components are as follows: the uprights, spindles, hubs, bearings, wheels, and tires, and the pictures shown here. My goals are to decrease unsprung weight with an emphasis on reducing rotational mass and inertia, increase adjustability, improve ease of manufacturing, and increase rigidity, particularly with the uprights. For the spindles, I've looked at these four configurations of hollow and solid, tapered and straight shaft, and this year we'll be using a hollow tapered spindle to focus on a lightweight design. That will be alloy steel for its high strength and reduced risk of failure. The front hubs, there are two designs I've looked at as a 4-bolt pattern and a splined option. The splined option, however, it's never been used at CSUN in past years, so this would require major design reanalysis. Also, the 4-bolt pattern is relatively easy to design and manufacture for CSUN's application. I've also looked at aluminum alloy versus a steel for the hubs. Aluminum would reduce weight versus the steel, and the strength is appropriate for our applications. The major change, as it's been said before, is redesigning the uprights. The previous 2 years have seen a fair amount of deflection in the uprights. To improve this, we'll increase rigidity and stiffness for continual use. Also, I've considered double shear joints for all the mounting points. To make it easier to manufacture, I will eliminate the need for a 4th axis CNC machining. Also, this will be done by using detachable and adjustable mounting point brackets. My design will ensure minimal kinematics geometry changes. 3 structures I've looked at are triangular, diamond, and I-beam shape. The past 2 years I've used the I-beam shape. This is where we've seen deflection. To reduce this deflection, we'll use a triangular and or a diamond shape. The diamond shape is lighter than the triangular shape relative with size and material. For the wheels, Kaiser wheels have been considered this year for changes. They are more rigid, lighter weight, and they have improved dimensional accuracy. However, they are much more expensive. The Bogarts we've used in the past 2 years, they are about a pound heavier, and they will each tire is kind of different from each other when they're manufactured because it's used on a manual lathe. For the Kaisers, I've looked at a 3-piece magnesium center versus aluminum center. The magnesium center is to reduce weight. This meets our goals for reducing rotational inertia. And wheels, the decision to go with a 10-inch wheel has been discarded due to it would require too many changes to the suspension components and possible other parts of the vehicle as well. The spline center locking wheel has also been considered, but as I said before, this would require a spline hub, which would also require major redesign and analysis, which is completely new to CSUN. So the 4-bolt pattern hub, or wheel edge, I should say, it's been proven reliable in the past. It's easy to design for our application, and it doesn't require changing any other components of the suspension. I've looked at Goodyear versus Hoosier tires. The Goodyear tires, we've seen better results with the compounds, and it's possible we would get sponsorship, meaning they would be cheaper than the Hoosiers. Performance-wise, the D2692 compounds versus the D2691s, we'll look at both compounds during our testing phase and decide which one we'll be using in competition. So my design proposal is a major redesign of the uprights with a triangular shape in the rear and a diamond shape in the front. This simplifies manufacturing, improves long-term strength, and decreases our risk of failure. A 4-bolt pattern hub and wheel will be used. Also the 13-inch magnesium-centered Kaiser wheels with the Goodyear tires. At this point, I'd like to transfer the presentation over to the controls department.